Today we're going to do symmetric encryption. And I had a funny comment at the end of lecture on Friday, which I really appreciated. After class, one of you came up to me and said, "Hey, we're trying to build an encryption algorithm. You taught us all this stuff about block ciphers, and then we walked away finding that using a block cipher is not secure because it's deterministic. So does that mean everything we learned on Friday was useless because it's deterministic, and deterministic doesn't provide secure encryption?" And I loved it, because the answer is yes. Everything I did show you on Friday was useless because it's deterministic, and deterministic does not provide in-CPA security. So today we're going to patch it up. What this shows you is that you can't use block ciphers alone for encryption. You need to do something more, and today I wanted to show you what that something more is. And in particular, we know that whatever we do can't be deterministic. So there's going to have to be something extra that puts in some randomness so that if you encrypt the same message twice, you'll get two different answers. All right, so I'm going to show you two standard ways of building secure encryption using a block cipher. And the block cipher is a building block that's going to help us do this. And the first way that I wanted to show you was CBC mode encryption. So let me show you how CBC mode encryption works. In CBC mode encryption, we have a message we want to encrypt. And we break that down into blocks. If I'm using AES for encryption, AES encrypts 128 bits at a time. So I'm going to break down my message into 128-bit blocks. The first 128 bits, the next 128 bits of the message, and so on. Okay, so let me call those blocks. P1 is the first block, P2, so on. And we're going to take our block cipher, maybe it's AES, and we're going to encrypt something with it. But it's not going to be P1 we're going to encrypt. What we're actually going to do is take the exclusive OR between the first block, P1, and this thing called an initialization vector, or an IV for short. And the initialization vector is what's going to make this not deterministic. We're going to choose, when we want to encrypt a message, we're going to choose a random initialization vector. It's just a random value, choosing uniformly at random. It'll be the width of a block, so in the case of AES, it'll be a 128-bit value. Every time you want to encrypt a message, you choose a new random value. So if you encrypt the same message twice, you're likely to end up with two different random values for the initialization vector, and that's what's going to make everything change. This exclusive OR, this represents bit-by-bit exclusive OR. Do you all know what the exclusive OR operation is? Does anyone want me to explain it? Okay. All right. So it's like addition modulo 2 at each bit position with no carries. So then we use the block cipher, like AES, and the result will be the first block of the ciphertext. Now we're going to do the same thing for P2, only we better not use that same initialization vector. What would be bad? Why would it be bad if I use that same initialization vector for P2? Yeah? Yeah, that'd be bad, because if P1 and P2 were the same, then C1 and C2 would be the same, and that would reveal some information about the message, and we don't want to reveal that. So we don't reuse the same initialization vector, but we got to use something. We want some value that looks kind of random, and so the idea is the outputs of an encryption algorithm of a block cipher look kind of random, so we're going to use that previous output. We're going to use that C1 value, and that's what we're going to use. Okay? And then we just keep doing that. So the encryption under the key K of the message with the blocks P1, P2, P3 will be, what do we send to the receiver to be able to decrypt? Well, we have to send C1 and C2 and C3. And to be able to decrypt, the recipient's going to need one more thing. They're going to need to know the initialization vector. So that's also considered part of the ciphertext. Okay, so the initialization vector is chosen randomly, and then it's included in the ciphertext. So that is called CBC mode encryption. And that is a way of building an encryption algorithm using a block cipher. So let's check that it meets the requirements for encryption algorithm. Well, you can see it can handle messages that are longer than 128 bits long, so that's good. Let's check whether you can decrypt. Can the recipient decrypt? Let's figure out how they would do that. They're going to need to know the key that's used with this block cipher. So we have some key that's used. It's a secret key known to the sender and the recipient. Assume the recipient knows the key and they know the ciphertext. Can they recover the plaintext P1, P2? Well, let's think about how they would learn what P1 is. They know what C1 is. The recipient knows what C1 is. And there's an encryption algorithm. Block ciphers, remember we said they're bijective, they're reversible, they're one-to-one. So there is a way you can undo the block cipher. You can do the decryption version of the block cipher if you know the key. So the recipient knows the key and knows C1, so they can obtain this value here. Now, can they obtain P1? Well, the idea is they know the initialization vector as well, so they can recover P1. You could think of it like subtracting off the initialization vector with mod 2 arithmetic with no carries. It turns out that subtraction and addition are the same thing, mod 2. So basically all you have to do is take this value, exclusive OR it with the initialization vector, and you'll recover P1. Okay, so that's how the recipient recovers P1. And then they do the same thing to recover the rest of the blocks. So take C2, run it backward, run through the decryption version of the block cipher, exclusive OR that with C1, and you'll get back P2. Okay, so this is decryptable.